2 trillion kilograms of steel are produced around the world every year, enough to construct 17,000 Bird's Nest stadiums, 31,000 Empire State Buildings, or 480,000 Guggenheim Bilbao skeletons. If all of this steel were to fill Central Park, this single ingot would be nearly 10 meters tall. If this steel were to wrap around the Earth, it would circle the equator more than 3 times. Our thesis begins at this global scale, by exploring the complex networks in which steel is embedded. The goal of this project is not the impossible task of exposing every detail of these tangled histories, but to question steel's material dominance around the world. This investigation is conducted through the lenses of 3 steel beams. While these beams are unique in their constructions and their contexts, they are all part of the tangled web of steel. The first story foregrounds geological and geopolitical issues of extraction. The second explores low-carbon methods of production and reproduction. The third examines the human and economic costs of the steel life cycle. We combine methods from scientific research and scenario planning to develop a speculation for each story, all cited 50 years in the future. These scenarios expand beyond the lenses of their singular beams to explore the complex networks of our ever-changing and challenging environment.
GBT 16270 was an extruded steel frame in the Huoshenshan Hospital in Wuhan, China, constructed as part of the government's response to the COVID-19 pandemic. It formed one of the many prefabricated panels that supported the 1,000-bed hospital, one of hundreds of large-scale infrastructure projects that the Chinese government undertook that year. China alone accounts for 51% of global steel demand, producing 996.3 million tons of crude steel, or 0.69 million tons per capita per year. 16270 began a lengthy journey to unite itself 13 billion years ago, when a star 50 times the size of our sun collapsed. In the final hours of this supernova explosion, iron and carbon, the fundamental building blocks for steel and human life, were forged. 4 billion years ago, these elements were united with the formation of the Earth, but they were not so evenly distributed across it. Carbon, in the form of coal, is both an essential fuel and a key reactant in the fabrication of structural steel. In 2019, the steel industry accounted for 15% of worldwide coal demand. 2 billion tons of iron ore and 1 billion tons of metallurgical coal were used to smelt 1.7 billion tons of crude steel. By 2020, China had become the largest producer of coking coal in the world, generating over 4 billion tons per year. The coal for 16270 originated primarily in China's Heirusu mine in the Inner Mongolia Autonomous Region, just one of the many water-stressed areas that supply 83% of China's growing coal demand. The remaining 10% originated in Australia, which supplies 55% of Chinese coal imports. Even before its formal creation, the raw material and power source needed to form 16270 had already traveled over 22,000 kilometers and passed through 5 customs checkpoints. On a molecular level, 16270 crossed many more borders before it united in Wuhan. 6 months before the light gauge frame was formed, its backbone was extracted from the earth in the form of virgin hematite. The black rock was pried from a vein in Australia's Roy Hill mine, a minuscule fraction of the 930 million tons of iron ore that the oceanic nation produces each year. Like most resources, 16270's ore moved along geopolitical channels. It was transported by BHP Group, one of the 4 companies that control 70% of the 2.35 billion ton global iron market. The ore was loaded onto a barge and shipped to China's largest port, the port of Shanghai. From there, the container was shipped 941 kilometers west down the Yangtze River. Finally, in the manufacturing center of Anshan, in Liaoning, 1 part iron united with 1 part coal. The fusion of materials of vastly different origins into a single high-strength alloy did not stop here. In order to refine the raw iron, manganese was added to the 0.5-ton beam. A single kilogram of the silvery mineral initially removed oxygen and sulfur from the ore. Another 5 kilograms of the same material was added later, as an alloying element, to impart strength and reduce brittleness. Like 62% of all manganese in China, this was an immigrant. It hailed from the Kalahari district in South Africa, which contains 70% of worldwide reserves. 90% of all the manganese in the world, for which there is no known substitute, is funneled directly into the steel industry. When these reserves are exhausted, China, the second largest producer of manganese and its largest global consumer, will have to find another way to refine and strengthen its steel. Ferroniobium, extracted from Brazil's Araja mine, which alone produces 80% of the global pyrochlore supply, was then added to further strengthen and reduce the weight of the steel. 45% of the world's ferroniobium is distributed across infrastructural and architectural projects, primarily in the form of HSLA steel such as 16270. The addition of just a single gram of this iron niobium alloy can reduce the weight of steel by 1 kilogram. In 2020, 16% of Brazil's ferroniobium mines were already under Chinese ownership. While the PRC could not yet geopolitically control all of the alloying elements of 16270, the superpower had begun to develop economic control of a global steel empire. After all of its molecules had been combined in Anshan, 16270 was dipped in a bath of molten zinc, searing its skin to protect it from oxidation. In Wuhan, cranes lifted it into the air, joining it to hundreds of other panels, a unitized system that would weather what would become a historic global pandemic. What would happen to the hospital in the coming years was, at the moment of its construction, unknown, but it was certain that global steel demand would continue to grow, and with it, a new era of territorialization. 16270 emerged at the dawn of the universe, but the materials of which it was composed were not universally accessible. The Steel Age was characterized not by a single atomic element, but by an amalgamation of the periodic table. No single nation could have unfettered access to all of the materials that make up this critical metal. Steel and its alloys were of the utmost importance to the tectonic, economic, and national security of nation-states, but this robust material was part of a fragile supply chain. The only way to control the steel empire was to expand beyond currently defined boundaries, to colonize nation-states and the Earth as a whole. Between 2005 and 2016, over half of Chinese international investments were diverted to energy and mining sectors in foreign countries. Sub-Saharan African countries attracted 1/3 of these funds. 500 of Chinese mining enterprises were in Zambia alone, where, since 2008, Chinese investors were exempt from local and federal taxes. Throughout the 21st century, China Baowu Steel Group Corporation Limited, then only the second largest steel producer in the world, continued expanding its empire. Fueled by fears that ore supplies would be exhausted by 2070, the conglomerate acquired 50 mines, supplying 13 types of metals and minerals around the globe. Eventually, the corporation amassed 99,000 square kilometers of land across 27 countries, a space the size of South Korea. On January 19, 2050, the National Assembly of Zambia formally granted 7 coal mines across the country to Baowu. The terms of the 200-year lease allowed for the new enclave territory to maintain 99% of the resources and profits obtained from the land. The Steel Age had ushered in a new kind of geopolitics, one based on resource ownership and economic systems rather than territorial boundaries. In March of 2070, the Mamba mine, located just 10 kilometers north of Lake Kariba and adjacent to the small town of Sinazongwe, reaches its peak. Coal mining productivity has increased 30% over the past 5 years to 9.8 tons per miner per hour. In the sweltering heat of Sector 924B, nearly 65 meters underground, a metric ton of anthracite coal is extracted from the exposed seam. The coal is transported via conveyor to the adjacent processing plant, where it will be separated from rocks, dirt, ash, and sulfur. Eventually, the coal will be loaded onto an automated tram, which will transport it 115 kilometers to the Choma distribution hub. From its incorporation in 2050 until present, Baowu has invested nearly $50 billion into infrastructure across Zambia, 90% of which exists within the boundaries of its own enclaves. The coal mined in this district will fuel Baowu's steel production, expanding the enclave into an empire. Once on the tram, the coal travels 20 kilometers north to gate D356 at the border between Baowu Enclave 03 and the Zambian Zimba and Choma districts. Superficially, this boundary is intended to be fluid, constantly moving people and resources in and out of the enclave. The artificial line is demarcated on either side by a 1 kilometer wide uninhabited zone. But the land is far from empty. Almost immediately after the establishment of the UIZ, a series of informal settlements emerged to support the roughly 5,000 miners that would otherwise have to travel 50-plus kilometers into the district on a daily basis. There's a tenuous standoff between the citizens of Baowu and of Zambia, a tense negotiation between economic investment and inequitable treatment. The UIZ is demarcated not by physical boundaries but by surveillance systems. A fleet of drones scan the area every 20 minutes, each drone ensuring, in 38.5 square kilometer increments, that the settlements neither formalize nor encroach on the official border. Baowu's permeable border ensures that the flow of people into the enclave is as heavily controlled as the flow of resources out. Since its incorporation in 2050, occupants of the UIZ engaged in a series of architectural protests, all aimed at subverting the surveillance state along the D356 highway, which cuts through the center of Sinazongwe and passes through the Mamba and Kolom coal mines. Only 1 kilometer outside of the mine, a Mars-hued liquid streams into the landscape. When the extracted anthracite is exposed to the air, sulfide minerals oxidize and release acid and heavy metals in the form of toxic mud. The enclave generates 500 tons of this sludge a year, which contains iron, copper, and 17 rare earth elements. This acid sludge is a hazard for the occupants of the enclave, but a valuable resource for occupants of the UIZ. It is funneled through a network of grooves in the land, an artificial intestine which allows further extraction from the extracted anthracite. The REEs will be used to make cell phones, rechargeable batteries, and GPS equipment. Byproducts such as manganese will be illegally exported to alloy high-strength structural steels. While the UIZ will reap the immediate financial benefits from these byproduct captures, they, both in the form of steel production and in the form of capital, which will be imported back into the enclave, will ultimately benefit the Baowu Empire. The tram continues 30 kilometers northeast, where it passes rocky outcrops and a hilly landscape. The rainy season once extended through April, but on this March morning the land has already been arid for weeks. Each ton of coal requires 250 liters of fresh water to produce, and each citizen within the enclave is allocated the same amount per day, well above the 100 liters that Baowu provides to native Zambians. In the UIZ, ridges in the land conceal a series of wells that illegally reach into the 20-meter aquifer. The corrugation on the well's earth-cast roofs provides structure and also directs the settling of coal dust. To the drones, these wells simply mimic coal tailing patterns already in the area. The surreptitious, supplemental water in the UIZ's reservoirs is barely usable, coated in a thin sheen of oil and coal dust. But there is no alternative for occupants of the UIZ, because the landscape has been diverted in service of the mine. As the cargo train rushes towards the Choma hub, it leaves behind a thick smog of coal dust in the air. In Sector 941C, before the dust can settle on the ground, it is captured by a screen network, rings of finely woven mesh that remove 85% of coal dust and sulfuric impurities from the air. From the aerial views of the surveillance drones, these circles simply look like outcrops in the landscape. The netted zones, which capture 20 grams of pollutants per square meter, provide shelter from the environment of the mine and enable the growth of crops which would otherwise have withered in the polluted air. The mesh is supported by a lightweight steel truss. Paradoxically, it is still embedded in the system of production that it attempts to subvert. The incorporation of Baowu 03 established a mining complex within an enclave territory, within a traditional nation-state, within a larger capitalist system. Vestiges of the enclave scar the landscape. The settlement serves as an informal critique of its autocratic government, of the proliferation of extractive landscapes, and of ownership of resources. As of 2070, there are still 200 years of proven reserves left in the mines. It is certain that the production cycle will endure. These follies are crucial to the survival of the settlement, but they also act as monuments to the loss incurred by geopolitical, geological exploitation, loss of life, of landscape, and of culture. The projects are unique in program but united in typology, a series of architectural masks that obscure their true function. They employ the materials of the new age of empires in order to hide from the geopolitical processes that enable their very existence.
A 992 was a custom steel H-beam in New York City's Fort Garr Museum. It supported the second-floor landing, providing visitors with a stable platform to view the museum's iconic bronze facade. The high-strength, low-alloy Colombian vanadium structural steel member was produced out of 3 flat roll sheets welded together at ArcelorMittal's Coatesville, Pennsylvania factory. The United States produces 3.5 million tons of structural steel annually, nearly 1.1 kilogram per person, in 12 structural steel mills across America's Rust Belt. 37% of all of this structural steel ends up in non-residential construction, like the Fort Garth Museum. On average, 69% or 61 million tons of US steel is produced from ferrous scrap. Recycled content for the structural steel is even higher, at 89%, but there are still carbon costs to low carbon method of production. A 992 had lived many lives before it was a beam. 80% of its composition came from the ferrous scrap. The remaining 20% of its composition came from prime steel shavings brushed off a factory floor. All these fragments were fused together in the electric arc furnace in Coatesville, Pennsylvania, which processes 900,000 tons of steel a year. Once A992 was fabricated, it was trucked to Eastern Steel Corp in Brooklyn, one of 35 steel service centers in the New York area. Over 70% of all the structural steel used in construction projects in the United States flows through some 1,120 service centers, which act as large warehouses. After only a few weeks in the service center stockroom, A992 was cut to length and trucked to 45 West 53rd Street, Midtown Manhattan, where engineers estimated it was supposed to stay as long as half a century. But in 2014, A992 was moved yet again. New beams arrived to support scaffoldings for workers to painstakingly dismantle the bronze facade panels. Oxyacetylene torches and reciprocating saws descended on the skeleton of the museum, severing A992 from its cross-bracing members. The remnant of the museum were loaded onto a flatbed truck and delivered to a metal scrap processors in Jersey City. A992 had become one of the 2.4 million tons of steel waste that New York City generates every year. Of the 100 tallest intentionally demolished skyscraper in history, 23 are in New York. 60% of them were steel structures. They lived for only 41 years, while the average lifespan of structured steel is 52 years. A992 lived to be 13. Even after just 13 years, the alloys that constituted the complex specification of A992 were lost. The beam was simply dragged to a scrapyard, where it was stripped of its cultural and technical identity. A992 would live again, but only after the wholesale destruction of its inherent self. Even in its diminished form, A992 remained a commodity. Due to rising demand in emerging countries, its masters found it more economical to ship the piles of scrap far away. A992 was ultimately trucked to the port of New York and New Jersey. From Newark, it was shipped 5,011 miles to the Turkish port of Machin, where it was forced to change its name to HS 70449, Ferrous Waste and Scrap. The 3.3-ton beam was just a fraction of 3.8 billion tons of steel scrap that the US shipped to Turkey each year, over 30% of US scrap. HS 70449 was melted down in an electric arc furnace owned by the Habas Group, one of the largest steel scrap producers in Turkey. The alloying atoms that had imbued A992 with its strengths were now considered toxin, too volatile to be recycled. It is unknown what happened to the rare minerals that were liquefied in the furnace, but the raw iron was extracted and turned into rebar, Turkey's most manufactured steel product. 27.5% of Turkish steel is exported as rebar. In 2014, 27.8% of this rebar was shipped regionally to the United Arab Emirates and to Egypt, but 20% returned to the United States. When A992 finally reached the end of its life, it was embedded in concrete. Pneumatic hammers broke up massive slabs of the rubble, recovering 68% of steel, but the remaining 32% was either destroyed in the demolition process or simply abandoned because it was deemed too costly to retrieve. A992, once a high-strength steel alloy, had been reduced to irrecoverable construction debris. A992 was reincarnated many times, sometimes before the end of its designated lifespan. It likely traced and retraced its steps many more times beyond what is outlined here. A992 weighted only 3.3 tons, a fraction of the 87.9 million tons of steel that the US was producing per year. Steel was lauded as being 100% recyclable, but moving even this comparatively small mass accrued a heavy carbon cost across many thousands of miles it traveled in its life. By 2020, half of all waste generated in New York City annually, roughly 6 million tons, was construction and demolition debris. In order to be recycled, steel was shipped to scrap processors and transport stations where they lay in wait for the highest bidder. Like A992, many pieces of structured steel traveled the globe to find a new home, a new economy willing to mass produce large amount of low-quality steel. In the continuous reforging that followed, they were doomed to lose the precious alloys for which so many landscapes had been mutilated. In order to build upon the city's 2020 goal to eliminate landfill waste within the next 30 years, the New York City Council enacted a radical piece of legislation. Bill S9502 banned the export of waste beyond borough boundaries, to take effect by January 2040. Manhattan, which generated astronomically more waste than it received, was disproportionately affected. By 2070, Manhattan had become the new epicenter of urban recycling. At 100 hours, a shadow passes over Bryant Park. An exoskeleton winds its way up the W.R. Grace building. Manhattan's latest rezoning has spelled certain doom for the iconic structure at 1114 6th Avenue, which will be the 27th mid-century building to be demolished in the last 3 months. In the early hours of the morning, robotic craws rip the building limb from limb. Curved and straight steel beams land on the back of a waste hauler, operated by one of the city's 250 public waste contractors. On this crisp March morning, over 1,200 haulers are roaming Manhattan's even-numbered avenues, blanketing the peninsula in a barcode of alternating pedestrian and supply thoroughfares. As the hauler continues up 6th Avenue, beam C17 jostles against an old Bertoia chair. After 40 minutes, the beam has reached the midpoint of the 47th Street Canal, one of 6 water wasteways that cuts 10-meter horizontal bends across Manhattan. Canal 47 begins at what was once the headquarters of the former United Nations, now the site of Amazon's 4th New York office. The waterway continues west through Hell's Kitchen, a 3,700-meter-long connective sinew between the residential and corporate neighborhoods. During the day, the area is a hub of pedestrian activity. Noise floats down from the roof terraces that form the extension of the High Line. But it is past the 10 p.m. curfew. The 602 digital turnstile will not scan pedestrian access codes until the sun rises. At 0200 hours, the hauler docks silently at one of the 8 garage ports on the south side of the canal. Under the terrace and under cover of darkness, 28 tons of waste from the Grace building are sorted by material. 60% of the waste is structural steel, to be classified as either reuse or recycle and then loaded onto a color-coded barge that will travel west towards the Hudson River, the southern artery of the wetwork. The 100-foot barge is just one of dozens, a parade of segmented bodies dotting the green water of the canal. At 0400 hours, a crane lifts the 2020 Toyota Camry 200 feet into the air. It was among the last private vehicles to exist within the city. The car is loaded onto the vessel, now a self-sustaining sorting facility that processes 28,000 tons of waste every day. Industrial jaws tear doors from chassis, limb from body, continuously deconstructing the object as it travels 16 stories down the gravity-fed honeycomb. Robotic arms shift through the pieces of flesh, sorting them according to size and material. In the steel section of this forensic lab, a small pieces of the Chemnitz shell is extracted and inserted into the Tesla mass spectrometer, where it is analyzed for its molecular composition. 6 centiseconds later, more craws grab the shell and divert it to one of the 452 conveyor belts radiating from the lab. The shell lands atop the frame of a forgotten treadmill and the 4.8-ton beam C-17. While distinct in form, these three artifacts are nearly identical in chemical composition. C-17 then passes over 30 active tracks at Hudson Yards to arrive at the electric arc furnace. Once nothing more than a parking lot, the 2.2-acre site has been transformed into Structure Inferno. Today, along with 120,000 tons of steel, the beam will be reborn again and again as the city relentlessly melts and remolds its steel. 0700 hours, a container vessel docks inside a warehouse at Pier 53. One of four 500 square foot holding pens for fresh steel. The steel is sorted according to composition and form, and sorted in this climate-controlled facility alongside overflow art storage for the former Whitney Museum, which was acquired by MoMA in 2047. An automated system continuously evaluates the accessioning and disaccessioning of steel. A new H-beam is rejoined by a forebear, one that was allowed it to bypass the furnace. Only a slight color difference indicates their distinct path. This morning, 8,293 beams stare out at the river, at a grid of vortex turbines that populate the Hudson, energy slaves to the 400 kilowatt-hour per ton furnace. The beams are protected from the corrosive air by the warehouse's synthetic skin, stretching over a screen made from 12,000 recycled steel rods. Soon, this steel will be called upon, dragged back to the water, to serve the counterclockwise cycle of unbuilding and rebuilding in this mega metropolis. By 0900 hours, a steel barge passes under the bridge at 61st Street. The bridge is a twin of that at Canal 47, Manhattan's answer to repairing its 100-years-old infrastructure. Each bridge is a part of recognizable set with bespoke connection to the existing building that support it. Simultaneously unique and generic, this replicable structure will save the city nearly $50 billion over the course of the next century. Technically, these net zero processes are considered green, and in 2080, the peninsula is designated the first ever LEED Palladium city. In 2020, the story of a single steel member is told over the course of a decade. By 2070, the reincarnation of a single steel member has been compressed into a single day. Manhattan is now the epicenter of an epidemic of melting and remolding steel.
GT 1499 was part of the Rana Plaza retail and apparel manufacturing complex in Dhaka, Bangladesh. By 2012, the number 6 reinforcing bar, nearly 8 meters in length, was combined with 246 identical pieces of low-grade carbon steel, a rebar cage encased in 8.18 tons of concrete. Because of its production efficiency and economy, reinforced concrete was often used in the Global South, which consumes just 23% of finished steel, despite holding 57% of the world's population. But the origins of 1499 were more complex than its simple form. Just 5 years earlier, it had been part of the 246,000-ton container ship Eurus London, which had sailed under the British flag since 1992. When the Eurus reached the end of its life, it, along with 674 ocean-going vessels, was sold to a scrapyard to be dissected rather than reused. Most of these ships landed on the shores of the Indian subcontinent, which accounted for 95% of gross scrap tonnage worldwide. In 2012, the 333-meter-long Eurus, which is one of 236 vessels to end up in a Bangladeshi scrapyard, beached at the Ferrous Steel Corporation shipyard in the Chattogram division. At this point, Bangladesh was recycling 7.52 million gross tons, or 34.5% of global ship scrap each year. Geographical features like the flat intertidal zone and stable weather patterns, coupled with low environmental and labor regulations, made the Bay of Bengal an ideal berth for 1499. Chattogram alone handled 20% of the world's total shipbreaking and produced most of Bangladesh's 5 million-ton steel demand. The Ferrous Steel Corporation was just one of 148 registered shipyards in Bangladesh, all of which were located on the 18-kilometer-long Silakundu Bhattiari coastal strip in northern Chattogram. It was from this 4,000 square meter space, which generated 60 to 80% of all the steel supply in Bangladesh, that 1499 would emerge. Like 45% of all container ships, the Eurus and 1499 would be reincarnated as rebar, encased in a concrete sarcophagus. Of the 45,000 ocean-going ships in the world, approximately 700, or 1.55%, are taken out of service each year. At 16 years of age, the Eurus was nearing the average lifespan of a container vessel, and, as the cost of insuring and maintaining the aging steel ship mounted, its value shifted from the goods it was carrying to the steel body of the vessel itself. At 246,000 tons, the same ship, which sold for almost $46 million in Bangladesh, would have fetched only $29 million in Turkey and $21 million in China. This discrepancy was due to the minimal infrastructural requirements, cheap labor, and high demand for recycled steel in a region with virtually no iron ore reserves. When waters rose with the spring tide on March 10, 2012, the Eurus's birth would signal its death. The massive tidal range of Chattogram, nearly 7 meters, allowed the ship to beach itself without the use of elaborate and expensive dry docks. The ship had a dead weight of nearly 250,000 tons, 95% of which was steel. But this steel was coated with 50 tons of paint containing lead, cadmium, organotins, arsenic, zinc, and chromium. Breaking a ship the size of the Eurus would flood the ground with 240 tons of molten steel. In the same process, roughly 5 tons of paint would be burnt in open air. Throughout its tenure, the Eurus had carried not just cargo, but 7.5 tons of asbestos and 881 tons of residual oil. This was just a fraction of the 79,000 tons of asbestos, 69,200 tons of toxic paints, and 240,000 tons of PCBs that Bangladesh was estimated to have imported between 2010 and 2030 in the form of decommissioned ships. Once beached, oxyacetylene torches dissected the Eurus's body, dividing it into truckable parts as demanded by their purchasers. Mechanical cranes lifted heavy equipment such as boilers, mortars, capstan stockings, while human arms carried metal plates, bars, or pipes to nearby stack yards. These arms were just some of thousands, between 22,000 and 50,000 direct laborers, and 100,000 and 200,000 indirect laborers, who were employed in the Bangladeshi shipbreaking yards. Here, on the shores of the Chattogram district, without respirators, helmets, or even shoes, workers endured risks ranging from toxic gas explosions to falls from the upper decks as high as 70 meters. Hatches contained flammable and explosive gases during cutting. Tubes carrying oxygen lay unprotected on the ground, vulnerable to falling objects and sparks from cutting torches. Virtually the entire scrapping process remained manual, minimizing costs but maximizing risk. After 5 months of backbreaking labor, the Eurus was gone. Parts of the ship were classified as casting scrap and re-rollable scrap, with the latter accounting for 90% of the steel extracted in the shipbreaking yards of Southeast Asia. The severed steel plates were shipped to one of 350 re-rolling mills along the Dhaka-Chattogram highway. Eventually, they made their way to Abu Khair Steel, the largest of the 9 sheet steel manufacturers in Bangladesh. The pieces were of high enough quality that they did not need to endure the heat of an electric arc furnace. Instead, they were sheared to size and reheated through a simple coal-fired furnace, and eventually rolled into reinforcing bars, including 1499. 1499 claimed thousands of lives by the end of its own. On April 24, 2013, the 7th floor of the 8-story Ranag Plaza garment factory began to crumble. When the overburdened and structurally unsound garment factory ultimately collapsed, it killed over 1,100 people. But the cost of reclaimed steel is undoubtedly much higher. In 2019 alone, 26 workers died, while over 150 were officially reported to be injured in the Bangladeshi shipbreaking industry. Shipbreaking was responsible for the extinction of 21 fish and crustacean species, and the endangerment of 11 other species in the region. An estimated 60,000 mangroves were cut down in the 14-kilometer stretch of coastline near Chattogram, leaving the coastline vulnerable to typhoons and floods. Shipbreaking was a paradox for the region, both an economic lifeline and a literal death sentence. This relentlessly degraded steel was part of a consumer cycle that valued economic consumption over human lives. By 2020, over 1.7 billion people were part of the consumer class, a group characterized by the accumulation of non-essential goods like those produced in the Rana Plaza factory. 90% of the world's trade was carried by sea on over 60,000 merchant ships. Global seaborne trade volumes exceeded 10 billion metric tons and an estimated 53.6 billion gross ton miles. After a 2018 agreement by the International Maritime Organization, 170 member states agreed to reduce their greenhouse gas emissions by 50% by 2050. But the efforts to green the shipping industry were countered by an already fatigued planet. Until 2000, the average Arctic sea ice volume was 3,302 cubic miles. By 2020, that number had dwindled to 1,480. Less than a decade later, shipping routes around the North Pole were established, allowing ice-breaking ships to accelerate the ongoing destruction. As the Arctic region became more accessible throughout the year, 17,735 nautical miles of shipping routes were added through 4 major passages. By 2050, Arctic shipping was estimated to reduce navigational distances between Europe and Asia by 40%, saving fuel and thereby reducing emissions by 64%. The subsequent increase in ship production corresponded to an increase in shipbreaking, which, by 2070, was increasing at a rate of 22% per year. (71.7, -0.6 degrees). On January 3, 2070, the HMS Lovecraft nears the end of its journey. The 50,000 TEU container ship had spent the better part of its life traveling the Suez Passage, delivering goods from the Dhaka Inland Container Port to Rotterdam, Netherlands. For the past 10 years, however, the Lovecraft was employed nearly 7,000 kilometers north, in what remained of the Arctic Circle. The melting process had been accelerated by increased icebreaking in the territory, until 90% of the ice shelf had permanently disappeared. A decade after it was retrofitted to provide safe waterways for bigger, more fuel-efficient cargo ships, the Lovecraft returns to the Arctic Ocean, its journey recorded by a series of AI buoys that monitor increasing ship traffic and a shrinking ice cape. This year, the Lovecraft is just one of the 1,130 end-stage icebreakers that will be severed from its battering prow and reinforced steel hull, temporary modifications in metal that permanently modified the natural landscape. 80.2, 32.5 degrees. The Lovecraft makes its final berth at Vitoya, the easternmost part of the Kingdom of Norway. Once almost completely covered by a 705 square kilometer ice cap, the now ice-free island is home to the largest of Norway's 6 shipbreaking yards. At 8 a.m., the Lovecraft docks in the Vitoya Ring, which scans the vessel and calculates precise divisions in its formwork. The ship is then conveyed to one of 3 200-meter-long automated shipbreaking jigs. A swarm of robotic claws descend upon the ship, dismembering it according to the specifications demanded by the ring. The claws work non-stop in the freezing air and through the polar night. In only 4 days, the Lovecraft is completely dismantled. At precisely 8 a.m. on January 7th, an automatic alert dispatches a cargo vessel to Vitoya, where it will be loaded with 640,000 tons of waiting steel. This deconstructed steel will be sold and shipped according to global demand. Vitoya processes nearly 100 ships per year, almost 10% of the global total. Technically, the island is still uninhabited, a paragon of environmental stewardship and laborless industry. 72.3, -157.6 degrees. 3,300 kilometers across the Arctic Circle is the Chukchi Sea, where an artificial archipelago marks growing territorial claims in the region. Rising waters and changing coastlines have exacerbated territorial disputes in the 200 nautical mile exclusive economic zones in the Arctic Ocean. In this space between the United States and Russia's Wrangel Island, the -1.6 degree water is dotted with ships, a stationary fleet that every day pumps 200 tons of sand from the ocean floor to supply the expanding atoll. 2 to 3 ships the size of the Lovecraft will pass through this water, murky with sand plumes, every year. US government subsidies will lead them to the shores of the Utjavik archipelago, where they will be broken and rebuilt into the fabric of the islands themselves. The steel extracted from these vessels supplies critical infrastructures to remediate oil spills, rescue damaged ships, and combat human trafficking in the region. But these islands are benevolent only at face value. Increased traffic has spurred increased pollution and disruption of the natural environment. Rather than recycle, the archipelago relies on external resources to survive, importing nearly $17 million worth of food and fuel each year. 70.5, -21.9 degrees. The environment is changing in many ways above the 66th parallel. At Itokutormit, on the east side of Greenland, the bay is now subject to disastrous storms and unusually high tides that occur as often as 20 times a year. Increasingly, ships are driven around on the rocky coastline. When shipbreaking supply outpaces demand, these vessels are deemed irrecoverable, doomed to weather the harsh Arctic elements for eternity. The H.H. Allegria is one of 2 vessels to run aground here in the last 5 years. The Allegria was completely automated, a space the size of 30 city blocks, with a crew of only 3 people. At its peak occupancy, it had a lower population density than Australia's Christmas Island. The crew was evacuated, but the ship was left for dead. The local community occasionally makes pilgrimages to the fallen soldier, harvesting what they need from its carcass and incorporating it into their homes. While habitable land on the shores of Greenland is expanding, the adjacent settlement still has a population of just 500 people, with annual steel use only averaging 36 kilograms per person per year. It will be at least a decade before the Allegria is completely consumed. 22.3, 91.8 degrees. The 26-kilometer shoreline of Chattogram district, once an expansive mudflat ideal for low-infrastructure shipbreaking, now abuts the eroding city. 67% of Bangladesh is less than 5 meters above sea level. Waters have risen above 1.5 meters, permanently altering the landscape. Only 20% of ships are still broken on these shores. The shipbreaking industry, which at its peak employed 300,000 people, now employs less than 50,000. The steel supply has dwindled, forcing those who would once have been employed in scrapping ships to mine landfills and demolition sites. But while lives are no longer lost in the shipbreaking industry on the shores of the Bay of Bengal, livelihoods have disappeared, and a select group of people are still trapped in a vicious cycle of consumerism and construction, enabled and reinforced by salvaged steel.
The scenarios we've outlined today acknowledge that extraction is not just a geological, but a geopolitical concern, that our current recycling practice is driven by capital rather than climate, and that life and livelihood is the true cost of consumption. They begin to investigate the spatial outcomes that might arise from an alternate approach to steel resource control, waste streams, and consumer culture. As populations grow and urban centers densify, so too will our material dependence. These three scenarios provide plausible futures that operate within the confines of the current capitalist system. They highlight the absurdity of our current practice without becoming absurdly unrelatable. The goal of scenario design is not to produce an alternative material, but to question the consequences of our current practice, while acknowledging that we, as designers, operate within a larger geopolitical context. While there are many disciplines involved in the global steel industry, architecture is still culpable. At 56%, the built environment is the single largest consumer of steel. In imagining these scenarios, we reconstruct our material culture and the effects that these speculations might have in the complex networks in which this material is embedded. They allow us to prepare for the future by providing a context for speaking about the unspeakable. While this thesis questions the pervasiveness of steel in the built environment, it is our hope that this reciprocal research design methodology could be expanded or applied to other issues of global complexity.